Right now, on March 19th, 2026, a ghost from another star system is refusing to die. Just a few days ago, the interstellar comet known as 3I Atlas completed a historic and deeply dangerous close encounter with the gas giant Jupiter. By every established law of celestial mechanics, thermodynamics, and cometary behavior, this ancient wanderer should already be fading into complete darkness. At a distance of more than 5 astronomical units from the Sun, the environment is a frozen, desolate vacuum. Solar radiation out here is about 25 times weaker than it is on Earth. Temperatures are collapsing, and the fragile, volatile core of the comet should be slipping back into the deep hibernation it maintained for billions of years between the stars. But the data arriving at observatories this morning tells a very different story. Instead of dissolving into the cold, the coma of Comet 3I Atlas, that vast glowing cloud of gas and dust surrounding its nucleus, remains unusually large, strikingly dense, and violently persistent. In fact, the first post-flyby observations show that the comet has become even more active. It is tearing itself apart, ejecting dozens of kilograms of water and complex organic molecules every single second into open space. It is as if the encounter with Jupiter delivered one final violent trigger, and now the object refuses to leave quietly. Yet as dramatic as this thermal anomaly appears, it is only the surface of the problem. The deeper mystery is hidden within the water vapor itself. The latest spectral data from the Atacama Large Millimeter Array and the James Webb Space Telescope has revealed a chemical signature so extreme, so out of place, that it challenges everything we understand about how planetary systems form. The isotopic fingerprint inside this escaping water is something we cannot reproduce anywhere in our own solar system. And within a matter of weeks, this object will disappear from our telescopes forever. So we trace the anomaly now, while we still can. Because by following this chemical trail back to its origin, we may finally understand why this comet is erupting, and what kind of alien ocean it was originally formed to become. To grasp the scale of what we are witnessing, we need to focus on the environment the comet is moving through. At more than 5 astronomical units from the Sun, a comet made primarily of water ice should be inactive. The physics of sublimation, where solid ice turns directly into gas, requires a minimum threshold of energy. And out here, that threshold simply should not be met. In our solar system, that energy threshold is typically reached at around 3 astronomical units from the Sun, a boundary known as the snow line. Beyond this distance, sunlight becomes too weak, and the photons simply do not carry enough energy to break the molecular bonds that hold water ice together. When comets from our own Oort cloud or Kuiper belt move outward past the orbit of Mars and toward Jupiter, their activity fades, their comas shrink, their tails disappear, and they become cold, dark bodies of inert rock and frozen ice. Comet 3I Atlas should be behaving the same way. Instead, it is doing the exact opposite, defying the energy limits of its environment. It is releasing dozens of kilograms of material every second. For that to happen, the comet must be tapping into a powerful internal energy source that has nothing to do with the Sun. The data clearly points to a thermal anomaly. But to understand where that heat is coming from, we have to look at the extreme gravitational encounter the comet just survived. A few days ago, its trajectory carried it deep into Jupiter's gravitational field. Jupiter is not just large, it dominates the outer solar system, controlling the motion of everything around it. As the comet approached, the side facing Jupiter experienced a much stronger gravitational pull than the side facing away. This difference creates what we call tidal forces. On solid planets, these forces cause only slight deformation. But a comet is not solid. It is a fragile, porous mixture of ancient ice, dust, and frozen gases, barely held together by its own weak gravity. As 3I Atlas passed through its closest approach to Jupiter, these tidal forces acted like a crushing grip. The entire structure of the comet was stretched and compressed within hours. The data now suggests that this process tore open deep fractures inside its icy nucleus. It broke through the hardened outer crust that had protected the interior for billions of years during its journey through interstellar space. But cracking the surface alone does not explain what we are seeing. Exposing ice to vacuum is not enough to produce continuous violent outgassing. It does not generate heat. So the question remains, where is the energy coming from? The answer lies in the state of the ice hidden deep inside the comet. In the near absolute zero temperatures of interstellar space, water molecules do not form the orderly crystal structures we see on Earth. Instead, they freeze into a chaotic arrangement known as amorphous ice. Amorphous ice is unstable. It naturally tends to reorganize into a more stable crystalline structure. When Jupiter's gravity fractured the comet, the shifting internal material created tiny bursts of frictional heat. For normal ice, that would not matter. But for amorphous ice, even a small temperature increase is enough to trigger a phase transition. As the disordered molecules snap into a crystalline form, they release stored energy in the form of heat. This process feeds itself. The heat released triggers more crystallization nearby, which releases more heat, creating a cascading chain reaction deep within the nucleus. This hidden mechanism is what is powering the massive coma we are seeing now. The comet is not being heated by the sun. It is consuming its own internal structure, releasing energy that has been locked inside for billions of years, triggered by the immense gravitational stress of Jupiter. And yet, even this does not explain the most disturbing part of the data. Because while this process tells us how the water is escaping, it tells us nothing about what the telescopes have discovered inside that water. In fact, once you understand the engine, the fuel becomes even more disturbing. The latest spectroscopic data from the Atacama Large Millimeter Array and the James Webb Space Telescope has completely overshadowed the thermal anomaly. Telescopes do not simply capture images. They break incoming light into its fundamental wavelengths, revealing the exact atomic and molecular composition of what they observe. Every element and every molecule interacts with light in a precise and unchanging way. By analyzing the glow of the coma surrounding Comet 3I Atlas, astronomers have been able to isolate the chemical signature of the material being released into space. And what they found in those spectral lines presents a contradiction that challenges our entire understanding of planetary formation. The data shows that the water streaming from the comet contains a deuterium to hydrogen ratio between 30 and 40 times higher than the water found in Earth's oceans. It does not match any known from our solar system. To understand why this matters so much, we need to step back and look at the structure of water itself and the history of hydrogen in the universe. Every molecule of water is made of one oxygen atom bonded to two hydrogen atoms. Hydrogen is the most abundant element in existence, formed in the immediate aftermath of the Big Bang. A standard hydrogen atom contains a single proton, orbited by a single electron. But not all hydrogen is identical. A small fraction of hydrogen atoms contain an additional neutron in the nucleus. This heavier form is known as deuterium. Because of that extra neutron, deuterium is roughly twice as massive as ordinary hydrogen. When deuterium bonds with oxygen, it forms what we call heavy water. Across the universe, the ratio of deuterium to hydrogen is relatively stable, set billions of years ago during the early stages of cosmic evolution. In our solar system, this ratio is preserved in oceans. Asteroids and comets. On Earth, out of 1 million water molecules, only about 156 contain deuterium. Measurements of comets from the Oort cloud and the Kuiper belt show similar values, with only minor variations explained by standard chemical processes in the early solar nebula. But Comet 3I Atlas breaks this pattern completely. A ratio 30 to 40 times higher means that thousands of molecules in every million are enriched with deuterium. This is not a small deviation. It is an extreme chemical signature that cannot be explained by any known process within our solar system. This isotopic anomaly is a clean fingerprint of a different origin, a different environment, a different planetary system, formed under conditions far beyond anything we have observed locally. To produce water, this enriched in deuterium, you need a very specific combination of extreme cold and immense time. The process responsible is known as isotopic fractionation. In the chaotic disk of gas and dust surrounding a young star, molecules are constantly colliding, breaking apart, and reforming. At moderate temperatures, regular hydrogen and deuterium behave almost identically. But as you move farther away from the star, into the coldest outer regions, temperatures begin to drop sharply. And as they approach near absolute zero, the small difference in mass between hydrogen and deuterium starts to matter in a very significant way. Because heavy water is slightly more massive, it exists in a lower energy state. In simple terms, it takes a bit more energy to break a chemical bond involving deuterium than it does for ordinary hydrogen. In warmer environments, this difference is negligible. The surrounding thermal energy easily overwhelms it. But in the extreme cold at the outer edge of a distant star system, where thermal energy is almost non-existent, that small difference becomes decisive. At temperatures of roughly 20 to 30 Kelvin, ordinary water molecules striking microscopic dust grains may still carry just enough energy to escape back into space. But heavy water molecules do not. They remain bound. They freeze onto the dust, over millions of years, repeating countless times. This process gradually separates the two. Lighter water is lost. Heavier water accumulates. And the ice that forms in these deep, dark regions becomes increasingly enriched with deuterium. Even so, the outer regions of our own early solar system never produced ratios anywhere close to what we are now observing, to reach levels 30 to 40 times higher than Earth. The material that formed Comet 3I Atlas must have existed in an environment far colder, far more isolated, and for far longer than anything we have directly studied. This suggests that the standard processes we understand simply did not apply where this object was born. And that leads to a striking possibility. Comet 3I Atlas may not have formed around a star like our Sun at all. It could have taken shape in the outer disk of a faint red dwarf, where the habitable zone is compressed inward and the outer regions are locked in a permanent, deep freeze. Or it may have formed in something even more extreme. It is possible that this comet originated within the disk of a rogue planet, a massive world ejected from its parent system while its moons and cometary material were still forming in complete darkness. Whatever its origin, this object carries with it a preserved record of a planetary system built under conditions radically different from our own. And that forces us to pause. Because what we are seeing is not just a comet. It is raw material from an alien world. If this deuterium-enriched water reflects the baseline chemistry of that system, then any rocky planets forming there and receiving water through comet impacts would have oceans dominated by heavy water. And that raises a deeper question. What would life look like in such an environment? Heavy water forms stronger hydrogen bonds than ordinary water. In high concentrations, it is toxic to complex life on Earth. It slows cellular division and disrupts the delicate folding of proteins. But what if life began in that environment from the very beginning? Could biology adapt to those stronger bonds? Could entirely different molecular systems evolve, stable only in heavy water? Would such life operate on a slower metabolic scale, shaped by a different chemical rhythm? These are not abstract questions. They sit at the intersection of quantum chemistry and astrobiology, where some of the most advanced research is happening today. And as scientists explore those possibilities, the data still streaming in from this object continues to deepen the mystery. The data now streaming in confirms that the comet is releasing far more than just water. Spectroscopic analysis shows that alongside the deuterium-enriched vapor, the comet is ejecting dozens of kilograms of complex organic molecules every second. The infrared instruments on the James Webb Space Telescope are detecting clear absorption signatures from carbon monoxide, carbon dioxide, methanol, and formaldehyde. These are not signs of life, but they are the essential chemical building blocks from which life can eventually emerge. And when these organics are found mixed with heavily enriched water, they begin to tell a much deeper story about the comet's origin. Billions of years ago, after forming in an environment only 20 to 30 Kelvin above absolute zero, this object was likely expelled from its home system. A close encounter with a massive migrating gas giant may have been enough to eject it completely, sending it drifting into interstellar space. For billions of years, it traveled through the Milky Way, fully exposed to the harsh conditions of deep space. High-energy cosmic rays, originating from distant supernovae and galactic cores, continuously bombarded its surface. These impacts shattered simple molecules such as water, carbon monoxide, and methane. In the extreme cold, those fragments recombined into more complex structures, forming heavier organic compounds. Over immense stretches of time, this process created a thick, dark crust of radiation processed material across the comet's surface. This outer layer acted as a protective shield, sealing in the pristine amorphous ice and its unusually enriched deuterium content. The comet became a time capsule, preserving the exact chemical conditions of its birth. It remained in that frozen state until its path eventually intersected with our solar system, drawn inward by the sun's gravity. It did not pass quietly through. Instead, its trajectory led it directly into the influence of Jupiter. And this is where its ancient history collided with present-day physics. As the comet now accelerates away from Jupiter, moving toward the constellation Gemini, the global astronomical community is racing against time. What we are witnessing is a final surge of activity, a brief flare before the object disappears forever. Its trajectory is hyperbolic, meaning it is not bound to the sun. Unlike planets or periodic comets that follow closed orbits, this object is moving too fast to be captured. Its path is open. It came from interstellar space, and it is already on its way back out. The encounter with Jupiter did more than fracture its structure. It altered its velocity. Through gravitational assist, the comet gained energy, stealing a small portion of Jupiter's orbital momentum as it passed. That interaction accelerated it beyond the escape velocity of the solar system. It is leaving, and it will never return. With every passing second, it moves tens of kilometers farther away. It grows dimmer, harder to detect, and increasingly difficult to study. Right now, observatories across the world are in a coordinated rush to capture as much data as possible. Scheduled observations have been interrupted. Telescopes that were pointed at distant galaxies and nebulae have been redirected toward this single, rapidly fading target. The James Webb Space Telescope is focusing its infrared instruments on the faint emission lines within the coma, attempting to determine how complex the organic molecules truly are. At the same time, The Atacama Large Millimeter Array is tracking the radio signals from the escaping material, measuring the flow of heavy water and mapping the structure of the fractures hidden within the rotating nucleus. But this entire observational effort is a race against time. The comet is moving rapidly outward into the far reaches of the solar system, and the sunlight illuminating its coma is dropping exponentially with distance. According to the inverse square law, when the distance doubles, the brightness falls to 1/4. What we are seeing now, this violent and luminous outgassing, will not last. It will fade into a faint glow, and then into complete darkness. Within a few weeks, Comet 3, I-Atlas, will fall below the detection limit of even our most sensitive instruments. It will disappear from view, leaving behind only data, and far more questions than answers. This narrowing window forces us to examine what we already know and ask more difficult questions. What if the sudden surge in activity after the encounter with Jupiter was not random, but the reactivation of processes that had remained dormant for billions of years? We began by asking how a comet could remain so active at more than 5 astronomical units from the Sun, where water ice should remain frozen. We also questioned how it could carry a deuterium signature so extreme that it contradicts everything we know about our own solar system. But when all the data is considered together, the contradiction resolves into a single, coherent explanation. The thermal anomaly and the isotopic anomaly are not separate. They are connected. The comet is active now because it formed in an environment cold enough to create that extreme chemical signature in the first place. Only in a region with temperatures around 20 to 30 Kelvin could amorphous ice remain stable for billions of years, preserving both its internal energy and its highly fractionated composition. In a warmer environment, that structure would have transformed long ago, and the deuterium ratio would have settled into something far more typical. What we are witnessing now is the release of that stored history. Jupiter's gravity acted as a trigger, compressing the comet and fracturing its protective crust. Inside, the ancient amorphous ice was exposed and briefly warmed. That was enough. The resulting chain reaction of crystallization released heat, which triggered further crystallization, creating a self-sustaining process. That energy is now driving the violent release of heavy water and organic material into space. The comet is not resisting the cold. It is consuming itself. It is releasing energy that has been locked inside since its formation, converting its own internal structure into motion, heat, and light. As the final streams of data arrive, we are left with a deeper realization. Comet 3 I-Atlas is not just an object passing through our sky. It is a fragment of a world we will never visit. A physical record of a planetary system shaped under conditions entirely different from our own. Could we be witnessing the final breaths of an ancient messenger, one that formed in a world where the chemistry of life and the architecture of planets followed an entirely different path? A path shaped by extreme fractionation, by conditions far beyond anything we experience here. Every molecule of heavy water, every complex organic compound now escaping into the vacuum, is a quiet reminder of how vast and varied the universe truly is. The processes that shape stars and planets are not confined to the narrow conditions of our own solar system. Beyond our local neighborhood, across the dark expanse of the Milky Way, there are environments defined by intense, cold, and overwhelming gravitational forces. Systems we are only beginning to understand. In just a few weeks, the glow surrounding this object will fade. The internal heat will dissipate, and the ancient ice, fractured and exposed, will return to darkness, carrying its secrets back into interstellar space. But the data it leaves behind will remain, and it will change how we think about what is possible. Not just here, but across the unseen depths of the galaxy.